This video is about Rolle's theorem. We're in the context of our calculus course. For our notes, we'll say this: let f of x be a function that satisfies the following conditions. First, f of x is continuous on the closed interval from a to b. Secondly, f of x is differentiable on the open interval from a to b. And thirdly, f of a equals f of b. If these conditions are met, then what this theorem says is that there exists a c within the interval from a to b that's open, such that f prime of c equals 0. There's a nice visual way, I think, to grasp this theorem, which is, let's go ahead and just make up a quadrant 1 graph. I'm going to put a and b on the x-axis. And of course, the conditions are such that f of a has to be equal to f of b. So if I put a dot above a to find f of a, then if I put a dot above b, it better be at the same elevation as that. So f of a equals f of b. That's like the y value for those points. Well, what this theorem is saying is that if f is continuous on this closed interval and differentiable on the open interval, and f of a equals f of b, which we have, then somewhere in this interval from a to b, we could find a c value such that f prime of c equals 0. Now remember, f prime of c equals 0, that would mean the derivative of our function at c is 0, which would mean it has a horizontal tangent line. And you can imagine this even visually. If I somehow connect from a to b with, you name it, I mean, as long as it's a smooth, differentiable kind of curve, which is what the conditions say above, and continuous, then try any variation. You're going to find at least one place where there is a flat horizontal tangent line. So you could have one or more places. This theorem says there exists a c, which means there's at least one. So even in a simple parabolic shape of this graph, there would be one maybe at the peak of that parabola or the valley, such that where f of c is, the tangent line is flat, which means f prime of c is 0. Let's try an example where we want to use Rolle's theorem, defined above, for f of x equals x plus 1 over x on the closed interval from 1/2 to 2. Now, as we know from what these conditions require for this theorem, we're going to have to find the derivative. Let's just start with that. So we want f prime of x given f of x here, which would be 1 minus 1 over x squared. That's coming directly from derivative rules on this f function. So let's check our conditions. Is f of x continuous on the closed interval from 1/2 to 2? That's the closed interval defined in this problem, and one of the first conditions for Rolle's theorem was that f of x has to be continuous on this. Well, as stated, f is this x plus 1 over x function. Now, the only place that this function would be discontinuous would be at 0, because you cannot divide by 0, but that's actually not within this closed interval we're looking at. So within from 1/2 to 2 in this closed interval, everything there is defined in a continuous way for this function, so we'll say yes, that condition is met. The next condition would be to see if f of x is differentiable on the open interval from 1/2 to 2. Well, this would be where the derivative is defined, but again, go look at our derivative that we've already found, and it's undefined when x is 0, but again, that's not within this open interval from 1/2 to 2, which means this condition is met. It would be defined anywhere else. Thirdly, we'd have to confirm that f of the left boundary of our interval 1/2 would be equal to f of the right boundary too. So if f of 1/2 equals f of 2, the third condition is met, and indeed that is true as well, as you could try by plugging those values in our function. They do give the same output. So, given that those conditions are met, what we're going to do to use the theorem is find the c value such that, as the theorem says, f prime of c equals 0. That's how we can use this theorem. So we already have f prime of x defined here as 1 minus 1 over x squared. We want to find out what c value is true such that f prime of c equals 0. So really we want to take our derivative function of 1 minus 1 over x squared and set it equal to 0, which is what this conclusion is supposed to find, and then solve it for x, and then that's going to be the c value that would make this true. Just to be extra clear, instead of writing 1 over x squared in this derivative that's equal to 0, I'm going to write 1 over c squared, because really we're trying to find the c value, which is an x value. Okay, so you could put an x there and then convert the answer to be c, but I'll just, to be clear, put a 1 over c squared, since we're really trying to solve for c now. Okay, this would mean 1 equals 1 over c squared, which would mean c squared equals 1, which means c is plus or minus 1. But if you go back to what this interval was given, remember we're stuck in the closed interval from 1/2 to 2, and -1 would not be in there, so I'll say not in the closed interval from 1/2 to 2, so we exclude that one and just say c equals 1. So the theorem guaranteed we could find some such c value, and we've found it given the setup and the conditions that were met.